where the edge density C goes to 0, we can take advantage of this sparsity to get faster algorithms. So using some greedy random sampling, we can speed up the speed up the runtime of the K-clique counting algorithm. And we get the following complicated looking runtimes, and apologize, it seems to be cut off at the bottom of the screen. In the graph case, so s equals 2, we can speed up this greedy random clique sampling technique with some fast matrix multiplication post-processing. But I'm not going to linger on this slide. Instead, I'm going to show you in pictures what exactly these runtimes are. But the takeaway is that the running times on Erdos-Renyi hypergraphs are very different, or can be very different, than the worst case. So let's look at what happens for hypergraphs, S-uniform hypergraphs with S more than or equal to 3. So in this plot, we have the y-axis is the running time of the algorithm, and the x-axis is k, and we want to count the number of k-cliques in our graphs. So you get this sort of intricate looking complexity from our algorithms. And we can ask, so this differs from the worst case complexity, but can we ask, is it optimal? Can we improve this? Why do we get this sort of strange looking curve? Which depends on the size k of cliques we want. And so we'll show that, in fact, if we assume that n to the k is the optimal worst case running time for counting k-cliques on these hypergraphs, we can deduce lower bounds on the running time of counting k-cliques on Erdos-Renyi hypergraphs. So if you look at the diagram now, we have a blue region, which we can show is infeasible. So there are no algorithms that run in this running time. And interestingly, it matches the algorithmic results that we have up to the k-clique percolation threshold. So this is assuming that the best, the exhaustive search algorithm for counting k-cliques in hypergraphs is optimal. And so this is really remarkable because the techniques that we use to show the algorithmic upper bound, this greedy random sampling technique, a priori doesn't seem to have anything to do really with the Fourier analytic argument that lies at the core of our lower bound. So it's interesting that we match the upper bound with our lower bound. And there is an open region after the k-clique percolation threshold. So it's an open problem to determine the complexity of k-clique counting in that regime for Erdos-Renyi hypergraphs. So we get this sophisticated average case complexity on Erdos-Renyi hypergraphs that follows just from a simple worst case complexity assumption. Now, I showed you the hypergraph case. The graph case is different because you can apply these fast matrix multiplication speedups. And in this case, if we assume that the best algorithm, the best known algorithm that runs in n to the omega k over 3 time is optimal for the worst case problem, we get the following infeasibility regime that doesn't quite match the feasibility. This is the algorithmic upper bound, and there is and it's open what the exact exponent should be in the running time for counting k-cliques on Erdos-Renyi graphs. But we can pin down that the exponent lies between these two curves. So now that I've sort of presented the gist of the results, let me motivate them. So why are we interested in this problem? So there's a huge body of work that studies clique problems on Erdos-Renyi graphs. So for example, finding cliques that are large in an Erdos-Renyi graph is presumed hard. There are no known polynomial algorithms. Similarly, finding large independent sets. An important problem is the planted clique problem. So finding whether if I hide a large clique in an Erdos-Renyi graph, finding it, recovering it, appears hard. And in fact, if we could prove it's hard, we would get many implications in statistics, and in particular proving that many statistical inference tasks are computationally hard. So it is an interesting problem to study, clique problems on Erdos-Renyi graphs. Now, ideally, we would want to base the average case hardness of these clique problems on Erdos-Renyi graphs on their worst case hardness. But unfortunately, there are known barriers against proving worst case to average case reductions for average case formations of NP-complete problems, such as the deciding whether it's a clique problem in this case. And so this would suggest that we would need to base hardness for problems like planted clique on average case hardness assumptions. But in this work, we work around this, and we will focus on a clique problem on Erdos-Renyi graphs that is in P. And we can show fine-grained average case hardness from the worst case. So our contributions are, one, worst case to average case reduction for clique counting, such that if we had a black box that counted k-cliques on Erdos-Renyi hypergraphs, then we could use it to count k-cliques on worst case graphs. And also analysis of several algorithms for k-clique counting, which I've sort of already mentioned. Now, I should mention an important related and motivating work from last year by Goldreich and Rothblum. This proves a worst case to average case reduction for k-clique counting, but in contrast to our paper, the average case distribution that they obtain is not an Erdos-Renyi distribution. In any case, the techniques are related, and we will see this later. So what's our main theorem? Our main theorem is a worst case to average case reduction with the following slowdown factor upsilon. So I like upsilon. Given a black box that counts k-cliques on Erdos-Renyi graphs with density C, with an upsilon multiplicative slowdown, with upsilon calls to this black box, we can count k-cliques on any worst case graph. So you will notice that there's some dependence on C and upsilon, and this is actually unavoidable because of our algorithmic upper bounds. So this polynomial dependence, if we could improve it, we would contradict the worst case hardness of k-cliques, of counting k-cliques in the worst case. So I apologize, lots of the things on my slide are cut off. Let's just restate the main implications of reduction. So if we assume the exponential time hypothesis, then essentially we get a net to the omega k running time lower bound for counting cliques on Erdos-Renyi hypergraphs. And if we assume the worst case algorithms are optimal, we get the following running times. Okay, so now let me just go over our proof techniques and give a proof sketch for this. So the proof is based on this trick by Lipton. It's a classical trick for proving worst case to average case reductions for computing polynomials. And so I'll show you how it works with the toy example. So in order to compute the permanent, we want to reduce computing the permanent of a worst case matrix, M, over some finite field, to computing the permanent on several matrices that are distributed uniformly over matrices over this finite field. So the idea is to consider the permanent of M plus XA, where A is a uniformly sampled random matrix. So for each X in the range 1 through M plus 1, the permanent of M plus XA is the permanent of a random matrix, because M plus XA is a random matrix. And moreover, the permanent of M plus XA is a degree N polynomial in X. And so if we can evaluate the permanent of M plus XA using our black box that works in the average case, then we can extract, using Lagrange interpolation, the coefficients of this polynomial and figure out what the permanent of M plus XA evaluated at X equals 0 is, and that's just the primitive m. So again, it's cut off. But, yeah. So, so this trick was used in classical complexity to prove that sharp P is hard on average, and only recently it was applied to fine-grained complexity. And so last year, Goldreich and Rothblum gave an application of this trick to K-clique counting. So they noted that the number of K-cliques in a graph with adjacency matrix A is given by the following low-degree polynomial. It's just the sum over subsets of the vertices of size K with the indicator that that subset is a clique. And this indicator is just the product of all of the edges between the vertices in this subset. Now, there is an issue with applying Lipton's trick to K-clique counting because we don't have access to the black box for valuing the polynomial P on random inputs over FQ to the n. So where the weights on the graph edges come from some finite field FQ, but rather we have a black box to valuing the polynomial on random graphs, where the weights of the edges are elements of are either 0 or 1. And so it's cut off, but so Goldreich and Rothblum get around this by essentially replacing each edge weight FQ, in FQ with a gadget that provides, for each weighted graph, provides like an equivalent unweighted graph. And so they deduce hardness of computing the number of K-cliques for some distribution of unweighted graphs that arises from this gadget-based reduction. But replacing each of these weights in FQ with a gadget seems to like it will inherently introduce some local non-uniform structure. And so in order to prove that K-clique counting on Erdos-Renyi hypergraphs is hard, we're going to have to do a slightly different thing. So what are we going to do? First, we're going to reduce the K-clique counting problem to K-clique counting on K-partite graphs. And we will use the special structure of K-partite graphs to eventually reduce down to Erdos-Renyi. So instead of working with the K-clique counting polynomial, which counts all K-cliques that are in this graph, we only count the K-cliques that agree with some vertex partition, V. If you look at polynomial P prime, it's only over the sum of K-cliques such that there's one vertex from each vertex set Vi in this K-clique. V1 through Vk is a vertex K partition. So in particular, we're going to, instead of considering general graphs, we're going to consider K-partite graphs, which are of the following form, essentially. For example, here you see a tripartite graph where there are no edges within each vertex set, V1, V2, V3. There are only edges between them. So, but the issue still remains. How do we get unweighted graphs from the weighted random graphs that we reduce to with Lipton's trick? And the answer is, well, binary expansions. So given a K-partite graph with uniform weights over some finite field, we can just write it as the weighted sum of some Erdos-Renyi graphs. And this is because of a lemma that's cut off, which essentially says that if we take an integer with a binary expansion such that each of the bits in this integer is Bernoulli C, then mod P, the integer will be very close to uniform. And this lemma is proved using Fourier analysis. So essentially, given a graph with uniform weights in FP, by rejection sampling, we can construct a binary expansion for these weights such that each of the elements in this binary expansion is an Erdos-Renyi graph, is a k-partite Erdos-Renyi graph. And now, finally, we combine this random binary expansion idea with the k-partiteness, the structure of the k-partite polynomial, to distribute just distribute the sum. And immediately, we obtain that the number of k-cliques in A is just a weighted combination of the k-clique counts in some Erdos-Renyi graphs, or approximately Erdos-Renyi graphs. And so in order for this to yield an efficient reduction, we need to bound the number of these Erdos-Renyi graphs. So for that, in fact, we can take M to be quite small, and that's part of the technical challenge, I suppose. And the reduction follows. So there are a few open problems. Currently, this reduction can only tolerate, polylogarithmically small error probability for dense, for k-clique counting on dense Erdos-Renyi graphs. And for sparse Erdos-Renyi graphs, the reduction can only tolerate polynomially small error probability. So can the error tolerance be improved? In fact, if we consider the problem of computing the parity of the number of k-cliques, we can improve this error tolerance when the graph is g(n)half. So it would be interesting to see if we can improve it even further. Moreover, we show the hardness of exactly computing the number of k-cliques in an Erdos-Renyi graph, and it would be interesting to see whether these techniques can be extended to show the hardness of approximating the number of k-cliques better than the concentration. Because, another question is, can we close the gap between the algorithms and the hardness results? So in the diagrams you saw there was an open region, so it'd be good to close that gap. And finally, are there other natural fine-grained hardness problems for which this simple random binary expansions technique can be applied to show hardness over uniform inputs in the hypercube? And so that's it. Thank you. Do you have any questions?